A silicon-controlled rectifier is a 4-layer solid-state current-controlling device. The name silicon-controlled rectifier is General Electric's trade name for a type of thyristor. The SCR was developed by a team of power engineers led by Gordon Hall and commercialized by Frank W. Bill Gutzwiller in 1957. Some sources define silicon-controlled rectifiers and thyristors as synonymous. Other sources define silicon-controlled rectifiers as a subset of a larger family of devices with at least 4 layers of alternating N and P-type material, this entire family being referred to as thyristors. According to Bill Gutzwiller, the terms SCR and controlled rectifier were earlier, and thyristor was applied later as usage of the device spread internationally. SCRs are unidirectional devices as opposed to TRIACs, which are bidirectional. SCRs can be triggered normally only by currents going into the gate as opposed to TRIACs, which can be triggered normally by either a positive or a negative current applied to its gate electrode. Construction. The silicon-controlled rectifier consists of 4 layers of semiconductors, which form NPNP or PNP structures. It has 3 junctions, labeled J1, J2, and J3 and 3 terminals. The anode terminal of an SCR is connected to the P-type material of a PNPN structure, and the cathode terminal is connected to the N-type layer, while the gate of the silicon-controlled rectifier SCR is connected to the P-type material nearest to the cathode. An SCR consists of 4 layers of alternating P and N-type semiconductor materials. Silicon is used as the intrinsic semiconductor, to which the proper dopants are added. The junctions are either diffused or alloyed. The planar construction is used for low-power SCRs. The maser-type construction is used for high-power SCRs. In this case, junction J2 is obtained by the diffusion method and then the outer 2 layers are alloyed to it, since the PNPN pellet is required to handle large currents. It is properly braced with tungsten or molybdenum plates to provide greater mechanical strength. One of these plates is hard soldered to a copper stud, which is threaded for attachment of heat sink. The doping of PNPN will depend on the application of SCR, since its characteristics are similar to those of the thyrotron. Today, the term thyristor applies to the larger family of multi-layer devices that exhibit bistable state change behavior, that is, switching either on or off. The operation of a SCR and other thyristors can be understood in terms of a pair of tightly coupled bipolar junction transistors, arranged to cause the self-latching action. Modes of operation. There are 3 modes of operation for an SCR depending upon the biasing given to it: forward blocking mode, forward conduction mode, reverse blocking mode, forward blocking mode. In this mode of operation, the anode is given a positive potential while the cathode is given a negative voltage, keeping the gate at 0 potential that is disconnected. In this case, junction J1 and J3 are forward biased while J2 is reversed biased, due to which only a small leakage current flows from the anode to the cathode until the applied voltage reaches its breakover value, at which J2 undergoes avalanche breakdown, and at this breakover voltage it starts conducting, but below breakover voltage it offers very high resistance to the flow of current and is said to be in off state. Forward conduction mode. SCR can be brought from blocking mode to conduction mode in 2 ways, either by increasing the voltage across anode to cathode beyond breakover voltage or by application of positive pulse at gate. Once it starts conducting, no more gate voltage is required to maintain it in on state. There is one way to turn it off, that is reduce the current flowing through it below a minimum value called holding current. Reverse blocking mode. SCR are available with reverse blocking capability. Reverse blocking capability adds to the forward voltage drop because of the need to have a long, low-doped P1 region. Usually, the reverse blocking voltage rating and forward blocking voltage rating are the same. The typical application for reverse blocking SCR is in current source inverters. SCR incapable of blocking reverse voltage are known as asymmetrical SCR, abbreviated ASCR. They typically have a reverse breakdown rating in the tens of volts. ASCR are used where either a reverse conducting diode is applied in parallel or where reverse voltage would never occur. Asymmetrical SCR can be fabricated with a reverse conducting diode in the same package. These are known as RCT, for reverse conducting thyristor. Thyristor turn-on methods: forward voltage triggering, gate triggering, DVDT triggering, temperature triggering, light triggering. Forward voltage triggering occurs when the anode-cathode forward voltage is increased with the gate circuit opened. This is known as avalanche breakdown, during which junction J2 will break down. At sufficient voltages, the thyristor changes to its on state with low voltage drop and large forward current. In this case, J1 and J3 are already forward biased. Application of SCRs: SCRs are mainly used in devices where the control of high power, possibly coupled with high voltage, is demanded. Their operation makes them suitable for use in medium to high voltage AC power control applications, such as lamp dimming, regulators and motor control. SCRs and similar devices are used for rectification of high power AC and high voltage direct current power transmission. They are also used in the control of welding machines, mainly MTAW and GTAW process. Compared to SCSs, a silicon-controlled switch behaves nearly the same way as an SCR, aside from a few distinctions. Unlike an SCR, a SCS switch is off when a positive voltage input current is applied to another anode gate lead. Unlike an SCR, a SCS can also be triggered into conduction when a negative voltage output current is applied to that same lead. SCSs are useful in practically all circuits that need a switch that turns on/off through two distinct control pulses. This includes power switching circuits, logic circuits, lamp drivers, counters, etc. Compared to triacs, TRIACs resemble SCRs in that they both act as electrically controlled switches. Unlike SCRs, triacs can pass current in either direction. Thus, TRIACs are particularly useful for AC applications. TRIACs have three leads, a gate lead and two conducting leads, referred to as MT1 and MT2. If no current voltage is applied to the gate lead, the TRIAC switch is off. On the other hand, if the trigger voltage is applied to the gate lead, the TRIAC switch is on. TRIACs are suitable for light dimming circuits, phase control circuits, AC power switching circuits, AC motor control circuits, etc. See also, dimmer, high voltage direct current, gate turn-off thyristor, insulated gate bipolar transistor, integrated gate commutated thyristor, thyristor, TRIAC, voltage regulator, snubber, crowbar, DIAC, BJT. References. Further reading, ON Semiconductor. Thyristor Theory and Design Considerations. PA 240, G.K. Mithil. Industrial and Power Electronics, K.B. Kanchandani. Power Electronics, External Links, SCR at All About Circuits, SCR Circuit Design.